In this lesson, we are going to move our attention to the conservation of energy equation, that is a statement of the first law of thermodynamics. For simplified flows where compressibility and heat transfer are not considered, the fluid is assumed to be isothermal, and the conservation of energy equation is not required. While in problems that involve heat transfer or compressible flows, this equation let us obtain the temperature of the fluid, and if the density is a function of temperature, we will also need an additional equation, namely an equation of state, to close our problem. Let's start with stating the first law of thermodynamics. The total energy change in a system equals the difference between the heat transferred to the system and the work done by the system on its surroundings. The Lagrangian form of this law is what we see here, where the Q term represents the heat transfer and the W term represents the work. Next, we are going to analyze in detail each of these terms and see how we can mathematically represent them. First, let's take a look at the energy and let's introduce the concept of energy per unit mass. The total energy is the combination of three forms of energy. The internal energy, that is a function of temperature. The kinetic energy, that is a function of the fluid velocity. And last, the potential energy, that is proportional to the fluid local elevation in the direction of the acceleration vector acting on the fluid. In this way, we can write the total energy as a volume integral of the energy per unit mass, or in terms of the three forms of energy. In order to close the energy equation, we need an equation of state and some thermodynamic relations. The equation of state connects the density to pressure and temperature. The most common example is the ideal gas law, where the density is the ratio of P to RT, where P is the pressure, T is the temperature, and R is the gas constant specific to the fluid. The ideal gas law applies to most gases at standard condition, like air or carbon dioxide. In case of non-ideal gas behavior, we need to state a different equation that is typically referred as the real gas equation of state. This equation can become very complex, and we are not going to consider this behavior in this course. In addition to the equation of state, we also need to introduce some thermodynamic relations, such as the internal energy, enthalpy, specific heats at constant volume and constant pressure, and their ratio. All of these relations are very important for compressible flows, but for the purpose of this course, we will not consider this topic in more detail. The rate of change of the total energy can also be impacted by processes that are not represented by internal, kinetic, and potential energies. In order to take into account these effects, we can add a source term to the equation. Typical sources can be radiation effects when we are dealing with very high temperatures, or thermal heating from electrical current flows. Let's now analyze the two remaining terms in the equation. First is the Q term, the heat transfer. Heat transfer can be defined as the heat flux across the boundary surface of the system. The primary mechanism of heat transfer is conduction. Introducing the Fourier's law of conduction, we can describe the heat flux term as the thermal conductivity times the temperature gradient. The last term remaining is the work. The work is done by the system on its surroundings and can be divided in two parts. One is the pressure work, done by the pressure acting normal to the system boundaries. As an example, we can consider the piston of an internal combustion engine, where the pressure of the fluid expanding after combustion pushes the piston back along the cylinder, creating the rotating motion of the crankshaft. The other form of work is the viscous work, that is done by the action of the viscous shear stresses, that we can consider as a viscous dissipation term. The viscous work can be also seen as a friction work that is transformed into heat. For high velocity flows, this term can create significant heat generation on the surface of a body. For example, imagine a re-entry capsule. The capsule will heat up re-entering into the atmosphere due to its high velocity. Part of this heating is due to the friction between the surface of the capsule and the air. Now that we have a mathematical description of all the terms in our equation, we can start and derive the Eulerian differential form of the energy equation. First, we apply the Reynolds transport theorem to convert the equation from the Lagrangian framework into the Eulerian framework. Then, we substitute the right-hand side terms with the expressions we defined before, and we apply the divergence theorem in order to convert all the surface integrals into volume integrals. Now we can assume that our control volume is completely arbitrary, so the sum of all the integrals must be equal to 0 in order to satisfy the conservation equation. In this way, we can achieve the differential form of the conservation of energy equation. For low-speed flows, the total energy per unit mass can be directly related to temperature, so the energy equation can be recast into an equation just for temperature. The set of equations that we derived so far, with the addition of an equation of state and suitable initial and boundary conditions, will allow us to model an entire flow field and solve for the unknown flow variables. This for a single-phase, compressible fluid with no advanced physics such as combustion or radiation. In later lectures, we will see how to impose suitable modeling assumptions to obtain mathematical models that can be solved.